Hi, this is Redesigning a Nozzle Test Stand by Team 23 and sponsored by Woodward. Our team consisted of 2 mechanical engineers, Andrew and Danielle, 2 electrical engineers, Michael and Ryan, and a computer engineer, Chris, with special appearances of Ruby Kaiser. Our team's task was to redesign a nozzle test stand. The machine shown is one of the oldest test stands Woodward has to test the quality of nozzles used for fuel injection in airplanes. These test stands essentially flow a test fluid through the machine and control many different parameters such as temperature, pressure, flow rate, and spray quality of the liquid. Some of the design issues of the old test stand in which Woodward wanted to change include the machine took up a large footprint of their floor. They tasked us with reducing this size and also eliminating inefficient use of space inside the machine. Many tubes and pipes block the operator's view, and when maintenance needs to occur, this is a problem. Another large issue Woodward had with this machine was there was little documentation on the test stand. For the electric panel, many components were nearly 50 years old and did not follow NFPA 79. Our team had a large focus on decreasing the overall footprint of the test stand on Woodward's floor. This included reorganizing the layout to increase ease of maintenance and supplying Woodward with complete mechanical, hydraulic, pneumatic, and electrical schematics. Some other changes our team made included completely redesigning the electric panel with new components and integrating a PLC and HMI into the new test stand. All the electric changes would adhere to National Fire Protection Agency 79, the electrical standard for industrial machinery. The following list outlined some of the electrical standards followed in the new design. Some out-of-scope design changes our team did not address include a chamber design for the nozzles to be tested into, and a spray angle measurement system. The cooling system and pressure generating system components were largely kept the same in our new design as they were in the old test stand. The following chart outlines many of the components that were removed from the old test stand and would not be reused in the new test stand. This chart outlines many of the components that would be changed in the new design of the test stand. These changes include changing filters, replacing the Coriolis meters and transmitters that control the flow rate of the test fluid, and eliminating many buttons and sensors that would be controlled by the HMI display instead. Our team started this project by generating different concepts of the position of the components needed. The first concept focused on decreasing the footprint of the test stand while separating the high and low voltages into 2 panels. The second concept utilized a 2-shelf design and uses more of the vertical space of the test stand for the purpose of reducing the footprint as much as possible. The third design focused on a more direct path of test fluid to flow in order to simplify piping and increasing the ease of maintenance on the machine. The 3 concepts were ranked against each other based on size, maintenance, ease of piping, and future space. After weighting these criteria and ranking the concepts against each other, Concept 1 was selected. Concept 1 was selected because of the reduction in size and ease of piping. Concept 1 also saved 648 squared inches of floor space. 2 electric panels are utilized in this design to separate high and low voltage. This allows operators to go into the low voltage panel without following arc flash gear requirement, which include wearing a face shield and leather gloves. A concept for the 2 electric panels was designed which had a focus on the ease of flow from one component to another and allowing for spare room for expansion. A design for the new test stand was then created. The test stand shell allowed for panels to be mounted in a space-efficient way. It also utilized vertical space with the help of shelves. The interior of the design was created with a focus on keeping maintenance easy while also efficiently utilizing pathing of the pipes and hoses. The interior of the design can now be seen without the test stand body. The front and back view are seen here. The cooling system placement can be seen in this figure. The inlet for the cooling agent can be seen in the top left, while many of the cooling components are placed at the bottom of the machine and the back right. The cooling system assembly consisted of a solenoid valve to turn on and off the system, while utilizing two heat exchangers to cool the test fluid. These heat exchangers were controlled by two control valves, which control the flow of the cooling agent. The pressure control and flow measurement systems mainly consisted in the middle of the new design. The pressure control system consisted of a series of different pumps to generate pressure and heat. The pressure then had a series of relief valves, regulators, and transmitters to achieve the desired results. RTDs were used to measure the temperature of the test fluid, and in conjunction with the temperature control system, the temperature was controlled. The flow measurement was mainly controlled by different chokes on the front of the machine and were measured through the Coriolis meters. Next, the pressure sensing and bleed system was mainly controlled at the top of the machine. After the fluid was measured by the Coriolis meters and choked if needed to control the flow, it was sent through valve actuators and filters before having the temperature checked a final time before being sent to the nozzles. The temperature needs to be between 78 and 82 degrees for this to happen. As the fluid goes through the nozzles, some of the pressure needs to be released. There are primary and secondary routes for this due to the different flow rates. The pressure is picked off and goes through a series of ball valves, snubbing valves, and pressure transducers. After some pressure is released, the fluid is sent back to the tank. A hydraulic diagram was created to show how each of the components connected to one another and to show the different systems being linked, such as the tank cooling system, pressure generating system, the flow control, flow measurement, and the pressure measurements. A more formal hydraulic diagram was also created. Our design placed the pneumatic system on the back left wall of the new design. Our design for the pneumatic system of the test stand has the air going from the shutoff valves to a compressed air filter before splitting off. The first route goes through a pressure regulator and then solenoids that control the ball valves in the machine. The other route goes through the pressure regulator and to a globe valve. The pressure regulator is paired with an electro-pneumatic transducer. This converts a current or voltage input into proportional output pressure. A block diagram was created for the pneumatic design to show how all the components link to one another. Here shows the front design of the new test stand. Many of the operational components can be seen here, such as an adjustment wheel to control the pressure of the system, while having a pressure gauge to see how much pressure is in the system. Different chokes can be seen to control the flow of the test fluid in both a primary line and a secondary line. The HMI screen allows an operator to turn on many of the pumps and lines inside the system. The HMI follows a state machine in order to find out when it is safe to test. When the machine is turned on, it is in the idle state. When the user turns on all three pumps in the system, the motor's on state is reached. Once the test fluid is in temperature and the machine is ready, the OK to test state will be reached. If the e-stop or if the fluid is ever over temperature, the safety not OK state will be reached and needs to be reset before going back to the idle state. Once the design was done, the test stand was then sent out to be manufactured. The material chosen was carbon steel, and the team chose to make the color ANSI 61 gray. The next few slides show the disassembling process of the old machine to prepare for the newly designed machine. The old test stand was then disposed of to make room for the new test stand. Now that the old test machine was torn apart, the new test stand could be put up. Many of the old components in the test stand were to be reused in the new test stand, and many of the parts were also returned to Woodward. The two new electric panels were then assembled. When the new test stand body arrived, the test stand could now be put together. The test stand shelves were inspected to make sure they would work when placed inside the machine body. After placing all the necessary components, the new design was finished. The inner cabinet had an easier to follow orientation while also taking up less of a footprint. The new front panel of the machine can be seen here. All the necessary commands an operator would need can be found here. Over the course of the senior project through Grand Valley, our team faced a few issues. Many of our team issues can be contributed to the custom piping needed in the design. That was all done by handheld equipment. Also, the lead times of different components in the machine body slowed down the process of the build. Although in the end, a new test stand was created for Woodward to replace their old outdated model that met a smaller footprint with complete documentation for mechanical, hydraulic, pneumatic, and electrical systems. Thank you for watching.